And we're back here with John Nelson. We're on the UMC-1600-H. Now, this is a 50 taper machine. It's 3+2 or full 5-axis, standard,
for sure.
And it's based on our EC1600 ZT model. So if you're familiar with our product line, you'll look at this and say, that looks a lot like an EC1600. That's because it is. So what kind of industries would be interested in a machine like this?
Certainly anything that's doing, any industry that needs 5-axis work on large, heavy parts, right? So oil and gas for sure. We've got several oil customers that use a very similar setup to this, and that's sort of what spurred the design of this machine. Also heavy industry, right? Forklifts, large trucks, anything like that.
Sure.
Large parts.
Large parts that need either 3+2 or 5-axis machining. Okay, so let's talk real quick. We'll just go through a few of the specs real quickly here. The travels are 64 in X, 50 in Y, and 40 inches in Z. So let's talk about the spindle, because that's really the highlight of this machine is the 50 taper spindle.
So the 50 taper, 7,500 RPM, 2-speed gearbox, 50 taper spindle. It's also got an optional 7,500 high horsepower, 60 horsepower spindle, or a 10,000 RPM, 60 horsepower spindle. So you can go either way with those spindles. But that 50 taper spindle really is the workhorse of Haas machines that are, doing a lot of heavy work around the world, really.
Yeah. So if you guys were with us, I think it was 2 days ago when Marcus and Andrew were on the EC500 50 taper and saw the heavy slotting that we were doing, that's a perfect example of the type of work that you can do on a Haas 50 taper.
Yeah, exactly. And it's the same spindle. As that machine.
Exactly. So let's talk tool changer real quick. Standard with a 30 pocket.
Yes, and optional 50, and also optional 120 pocket chain style tool changer, which is new for us.
Yep,
for sure.
That's a new addition for us. Let's see.
This machine, sorry to interrupt you, this machine has the 50. I'm not sure if you want to walk around and show it.
We can show it at the end, I think, once we get Sal around there. So I think, Sal, you want to come in here? Because we're going to talk about these rotaries, which is really the highlight of this machine. So 630 millimeter diameter rotary on the 5th axis. So I'm going to let you talk it through.
Is the 630 millimeter diameter, and the through bore on that rotary is 10.125 inches, right? The rotary itself comes with, and if we could sort of sweep around here, Sal, and show a little side view, you can see that this rotary has the T-slot table, right? That's the standard table that comes with this rotary. It's 8 T-slots at 45 degrees around that, radial T-slots around that rotary, but it also has a couple of options available. You can get a drilled and tapped faceplate with circular drilled and tapped hole patterns, and you can find that in the machine layout drawing for more information on that. Or you can get an A1-20 spindle nose if you're always going to use a chuck, either 3-4 jaw chuck, maybe a pneumatic chuck for automatic operation. You can get a spindle nose as the permanent mount to that rotary as well.
Okay, and there's, Frank, if you don't bring the website up yet, but if you can get it ready, we've got some machine features.
So Sal,
if you can come in again.
Get a close up in here. So this face, this surface here, and tapped holes here are machined to accept the optional T-slot tables that can bolt right to this. Now they're about as wide as that surface is machined, to give you an idea of how wide that is, and they come out in 2 different lengths, which we have more information on the website, but you can get those, and then those are an additional support for a steady rest, an A-frame support, or maybe even a tailstock.
Right. So 2 different table lengths and multiple different supports. Tailstock, steady rest, etc. Okay. All right, Frank, you got that up on the website? Okay, good. Think you can come back now?
So I did want to mention that engineering has tested routing of pneumatic lines, 1/2-inch diameter, OD diameter pneumatic lines, or I guess number 4 size hydraulic lines, 2 of them each, through through the rotary configuration so that you could attach an air chuck or hydraulic chuck to this rotary.
Yep, so nice clean routing up through the center.
Yep.
Okay. Travels, let's talk travels real quick. And maybe when you do this, do you mind grabbing the
sure,
remote
I'll grab the jog handle.
It's a big machine. He'll be back in a minute. Here he is. Okay. So we're going to talk rotary travels.
So let's see here. Sorry.
Oh, we got to go into handle jog mode. So the C-axis
sort of helps when you put it in jog mode first.
Yeah, it does. So the C-axis is full 360 degrees of rotation, right?
C will give you the. Excuse me.
There we go.
Had to wait for the brake to release. C will give you a full 360, basically unlimited rotations on C. And then the B is plus or minus 120. Right now, we are all the way pegged at minus 120. And then I'll head back over towards 0. And then spin it around and you get an idea. So there's where you can route your cables for your hoses for pneumatic. And then you'll see that we have a machine surface on the side of the casting here that you could put a vise. This is a Haas 6-inch vise that bolts right up there. That you could do extra work if you needed to. You could use this for something else. If you didn't have big parts to run, you could still run some parts over here. However you wanted to utilize it, but it's machined, it's square, and when this thing's set at minus 90, it'll be facing this.
And I'm throwing a curveball at you because we didn't talk about this beforehand, but you mentioned the brake on the rotary.
Yes.
And I wonder if you could talk about that from a programming standpoint.
Oh, yeah, thanks. So let me drop this off.
Hold, please. We'll be right back. Some music.
So, sorry about that.
It's all right.
We didn't rehearse this part, folks. Sorry. The rotary brakes. So there's a command to clamp the 4th axis brake, which is M10, clamp the 5th axis brake, M12. Release the 4th axis brake, M11, release the 5th axis, M13. So those are, a lot of times post-processors will output all of those clamps. But those codes are really unnecessary unless you're going to do a simultaneous toolpath. And here's what I mean by that. When the Haas control sees a command for a rotary axis, it knows automatically that it needs to release the brake to make that move. And when that move is complete, if there's not another rotary axis move on the block right after it, it's going to clamp that brake after the move is complete. You don't have to worry about brakes, turning them on, turning them off. Where you do need to be concerned is if you're getting ready to do a simultaneous 5-axis toolpath where you're going to have a whole bunch of blocks in a row that are going to have rotary moves, but you might have some interspersed in there that don't have a movement on 1 or 2 or 3 blocks.
Right.
Well, your nice smooth rotary axis, nice smooth simultaneous 5-axis motion is going to stop and wait for that brake to clamp because there was no axis move on that block.
That's right.
So that's why you want to use the M code to unclamp the brake at the beginning of your toolpath so that the control doesn't try to clamp or unclamp when it sees a block with or without a rotary move.
And that can have a huge effect on cycle time.
Exactly. That could make your part's going to look terrible. Your cycle time will take forever. So anytime you're doing a simultaneous 5-axis toolpath, unclamp the brakes at the beginning of the toolpath and make sure that you clamp them again at the end, because if you unclamp a brake with an M code, it's going to remain unclamped till the end of time or until you cycle the power on the machine.
Right.
So, or that you reclamp it with the M code. So the only way to clamp it once it's unclamped is clamp it with the M code or cycle the power on the machine.
Okay, good.
Okay.
Thanks for explaining that.
No problem. No problem.
Threw that in there. We had talked about it the other day. So
yeah.
Okay.
It really does increase cycle time. Sorry.
Yeah, you had talked about
M codes.
You had done a program.
You can only have one M code on a block.
That's right.
So if you have to release the 4th axis brake, that we have to wait a second and a half or whatever the brake release time is, and then the next block gets executed for the other rotary axis.
you're waiting again.
But if you have a block of code, if you're not using the M codes to release the brakes, you have a block of code that has both rotary axis moves on it. They both unclamp at the same time, they both move at the same time, and they both clamp at the same time. And that can save you seconds every time you index, 3 seconds every time you unclamp, move, and reclamp.
Right.
So it's a big deal to not have all of those M11, M13, M10, M12s in your program when you don't need them.
Right. Okay, thanks for explaining that. So brake torque, each of the brakes on this rotary have 4,000 foot-pound of brake torque.
Massive, massive.
Huge amount of brake torque. I think we want to talk about, because there are some tight areas in here depending on the size of your part, and we've been emphasizing this on all our 5-axis machines, that you really need to be familiar with the machine layout drawing.
Yes, yes. Study the machine layout drawing. Because the because the tool axis is fixed along Z, it's not quite as important on the tilting head as it is on the tilting head machines.
Right.
But still, you need to know your rotary stack up, right? So when I was setting up this demo, I needed to know the thickness of my spacer, the thickness of my chuck, the width of my jaws, and then where my part was,
right,
before I could tell if I was going to have enough room. And so you really have to have a good idea in your mind when you're trying to figure out, will my part fit, what your actual work holding setup is going to be, and where your part's going to be in space once you get to
and
rotate
you know, we quickly talked about some of the other options like the tables and the steady rests and things like that. If you go to HaasCNC.com and search UMC-1600-H, you'll get the machine layout drawing. There's a details tab on there where you can look at all the optional work holding. We didn't do it justice. We kind of glossed over it.
Yeah,
but
yeah.
That's where you'll find everything.
We did pass by the weight specification. So you can put 1,500 pounds on this rotary when it's unsupported. And if you have the extension, T-slot table extension and an A-frame or steady rest or something, you can put 3,000 pounds up there.
Okay, 15,000 unsupported.
1,500.
15,000. Wow, added an extra zero in there.
Yeah,
that's important.
1,500 unsupported, 3,000 supported.
Okay, great. Let's see. This is now, you talked a little bit about post-processor. I can't speak today.
Yeah, post-processors. So this is essentially a UMC, right?
Right.
The only difference between this machine programmatically, right, writing programs for it, and axis orientations, the only difference between this machine and a UMC-1000, for example, is the fact that this machine, the B axis, has plus or minus 120 degrees of travel, whereas it's limited to less than that on the UMC-1000.
Right.
But as far as posting code, generating code for parts on this machine, the same exact post processor would work fine. Adjusting the travel limits in a post processor is a very minor thing. Most guys can do it themselves, or you can get your post supplier to do it really, really quickly. It's not a big deal. But essentially, it's a UMC.
Right.
Same orientations of axis and all that.
It's good to know. Okay, let's talk about Vps templates.
Oh yeah. So we created a custom Vps template for this machine, and it essentially runs the same probing cycle code that you would use on any UMC. But the template to begin with is different because the layout of the rotary looks different.
Right.
And the standard rotary axis calibration tool, you know, the stem with the ball that we supply with all of the rotary products, doesn't fit on this machine because it's so big. So we made a special longer base for that rotary axis calibration tool, so it'll go across that 10-inch diameter hole through the middle, and you can program in the middle. And then there's actually a special thing I want to point out if you're using an older magnetic base tooling ball with a stem on it there. So Frank, if you could bring up the control over here, I want to walk around to the control and go over to the VPS template, down to probing, down to calibration, or sorry, down to custom. And here's the MRZP template to set MRZP on the UMC-1600-H. There's our template, so you can see the image there of the rotary axis calibration tool where it's got the straight artifact. And if I have that one, I'm going to bolt it up there and press the S key. But if I have the old magnetic base with an angle on it, I am going to go ahead and press the M key. And then it's going to show me this image. And really what this means is that I have to place that magnetic base at a 45-degree angle, pointing either down or up, and it needs to be on the right side of center line if I'm the operator looking straight at the rotary platter. The red zone, I can't put that mag base anywhere else in the red zone or I won't be able to reach that ball. As the B axis rotates around, that tooling ball will actually be too far away for the probe to actually reach the ball. So it needs to be on the right half, and it needs to be in that 45-degree zone, either on the upper right quadrant or the lower right quadrant. And that's really the difference between the template for setting MRZP on UMC-1600-H versus setting MRZP on any of the other UMC models that we have. Okay.
All right. I was standing there trying to listen to you.
Sorry
in case you guys see us kind of trying to get close to each other here. We're actually out in the factory. They're still running the machines over here. We're building machines over here, so it's a little bit loud. So there was one more thing before we go to the demo. We are going to show you a demo, and you're going to talk through it like you did on the Duo. But you wanted to talk about setting 335.
Yeah, so setting 335. I mentioned it the other day when we were over at the VR8.
Yep.
I'll mention it again. Setting 335 is linear rapid mode. It's been in controls, next generation controls, for almost a year now, I think. But I mention it now because very, very soon all machines will be shipping with this setting set to linear XYZ. The setting can be set to 3 different positions. The first is none. The second is linear XYZ, and the third is linear plus rotary. Now, a little bit of history. Since the very beginning, all Haas machines went in a G00 rapid positioning command. Any axes, if there are more than one axis move on that block, both axes would start towards their endpoint at the same time at the same speed. So essentially, it traveled away from the start point at a 45-degree angle until the axis with the shortest distance to travel reached its endpoint. Once that axis reached its endpoint, it would stop, but the axis with the longer distance to travel would keep going. And what you got essentially was a dogleg rapid move. So it was a little less predictable, actually very unpredictable, exactly where that tool was going. Linear rapid mode, what we do is we slow the speed of the axis with the shorter distance to travel, and the axis with the longest distance to travel goes at full speed. So it doesn't take any longer to get there. It's just that we get there by traveling in a straight line. All the axes start at the same time and end at the same time, giving you a straight line. You can do all 3 axes and get a diagonal move. That's fantastic. So the 3 settings again are none. If you set it to none, it's going to behave like all the Haas machines that we built since the beginning of time. If you set it to linear XYZ, then we are going to, the linear axes are all going to, if they're programmed in the same block, will start at the same time and end at the same time, essentially giving you a straight line move. If you set it to linear plus rotary, which we will set it to on machines that have built-in rotary axes like this one, then all the axes that are on that particular G00 block will start at the same time, end at the same time. And what this does is give you a much more predictable path. It's super important in 5-axis, especially on tilting head 5-axis machines, where the tool is moving around and the workpiece may be moving in some of the axes. So, so it's a much more predictable move, and believe me, if you've been running Haas machines with dogleg rapids forever, and you turn setting 335 linear rapid mode on, you're going to love it. It's going to be a little different at first, but I think you'll really like it. And I wanted to mention it, and also wanted to make everyone aware that it was coming, that machines would be shipping with it set on in the very near future.
Okay, do we want to go to the demo?
Yeah, let's do that. Let me run back over here.
John's going to head over there. So Sal, if you want to come around here. And we're gonna go to the demo here shortly, but so John, you want to talk about before Frank starts here? Sorry, I just walked out of frame.
Yeah, so the actual, this part is an actual ductile cast iron part that we use in the factory. This is the B-axis gearbox subplate used on EC400s and 500s. My program doesn't make our actual part because there's no 5-axis tool paths on the actual part that we make. But I was able to use the shape of this casting and the size of this casting to show off this machine and to program some 5-axis moves. The OD of this part is 23.8 inches and the ID is 13.5. That casting is 2.68 inches thick. And we had the machine shop face the backside and rough the bore to clean it up so we could grab it on our on the ID with our manual 25-inch 3-jaw chuck. I used Fusion 360 to program this part. This was the first 5-axis that I had done in Fusion, and I just want to give a little shout out to my buddy Angelo Duras, who I've known for a long time. Really helped me out with pro tips during programming. This is very, very cool. Thanks, Angelo. So all of these cutting tools and tool holders in this demo are available on HaasTooling.com. I programmed all the tools right in the middle of the recommended speed and feed range. There's definitely room to go up a little faster or down a little bit slower, but the purpose was to show that, hey, if you start right in the middle of the range, you're going to get good parts right out of the gate. You don't have to think about anything, and there is room to optimize. So we are looking at, this is a 2.5-inch length of cut, 3/4-inch 5-fluter that's doing a swarf tool path around that angled surface. We're going to come back over and put some chamfers on it. I'll ask Frank to restart our demo again. When we get to that point, it'll just be another few seconds here, and I'll talk about some of the cutting tools right from the very beginning of the demo. By the way, excellent edit by my buddy Tyler on this thing. All right, so here we're going again. We're going to get to this first cutter is going to be the, oh, sorry, we're loading the part up there. The first cutter here is a 1-inch 4-flute going around the OD. That thing is cutting, it's cutting, let's see, sorry, it's cutting 400 thousandths per side off of that cut and all the way 1.5 inches deep. Running at 1566 and 35 inches a minute. Our shell mill here, that's an HS6 NP 90-degree shell mill, obviously Haas shell mill. It's 2.5-inch diameter 5-flute. We're running that at 700 surface feet and 10 thou chip load. Each of those cuts is 200 thousandths deep. Love this cutter, cut really great. Ripped that cast iron like it was nothing. You can see the good chips there. Next tool is a 1/2-inch drill. That's actually a TSC drill, but we drilled it dried in this cast iron to show those moves. That's 4,100 RPM, 11 thousandths per revolution. So this tool is a 1/2-inch 5-fluter. Again, programmed right in the middle of the recommended speed and feed range, 410 surface feet and 5 thou and 6/10 chip load. For roughing and finishing pockets here, we're going to get to, now this is a 3/8 inch and we're finishing a swarf toolpath. So we're putting a 5-degree angle on the walls of those pockets around those curves. So that's the full 5-axis toolpath you're looking at there. Again, a 3/8 inch 5-fluter, 48 inches a minute around there. Now we're back to that 3/4 inch, 2.5 inch length of cut 5-fluter that's finishing that angled surface with a swarf toolpath. And then our chamfer tools coming in here, they're running at the max RPM, 7,500, and just to put the finishing touches on our demo. And that's it.